Hello everyone. In this section, we're interested in talking about optimization problems. What is an optimization problem? But really an application of our ability to find maximum or minimum values for a given function. Now, most of the time, those given the given functions that we've dealt with so far have been, well, just that, functions that have been given to us for which we've found the derivative and then determined things like critical numbers, where the derivatives are either equal to zero or undefined, and determined whether or not we had a maximum or a minimum. And some of the times we're able to draw a graph or some other thing to represent that. But we might have sort of a different issue depending on the function. So let's talk about just a few types of problems where maximization or minimization could be applied. One might be this. A farmer plans to fence in a rectangular pasture adjacent to a river. If the area of the pasture is fixed, what dimensions will require the least amount of fence if no fencing is needed along the river? Well, there's a key word right there, one that comes up all the time when we say something like least amount. We're asking to minimize something. We're trying to find a minimum. So we would have to have a function that would do that for us. So we would need to find a minimum there. What else? Well, here's one, the function that describes traffic rate. It's kind of interesting, but on any given day, the flow rate of cars on a congested highway is given by the formula F, which is the flow rate, equals V volume over 22 plus 0.02 V squared, where V is the speed of traffic in miles per hour. So we're asking, well, what speed would maximize the flow rate along this road? Supposedly somebody might have done a study somewhere and found this function describes it perfectly. So we would want to be able to find that value. Here's another situation, sort of an interesting mathematical one anyways. A right triangle is formed in the first quadrant by the x and y axes through a line through the point 1, 2. So we have this triangle that's formed, this right triangle. We might ask, well, what coordinates of the x and y intercepts will produce a line of minimum length, right? So we would want to be able to find a minimization. So minimization, maximization, this is our goal. How do we handle problems like this? So to start it all off, let's start out with an example that seems pretty straightforward. And that is this. Find a point on the graph of a function, f of x equals x squared, that is closest to the point 2 comma 1/2. So, all right, we've got an x and y coordinate. 2 1/2 is certainly not on the graph of f of x equals x squared. So we might ask the question, what are they after here? We're looking for a point on the graph that's closest to a point, so we're looking for a distance. Well, here's sort of the situation in miniature. Here's my graph. I've got y equals x squared right here, and we have the point 2 1/2 right here. We're saying, all right, we could draw a line at any of these points along the curve and then find the distance from that point to the point 2, 0.5. The question is, which of these will be closest to the point? So there's certainly some xy coordinate point in here that we're looking for that's going to give it to us, right? And we know every coordinate along this line right here, y equals x squared, right? It's going to be the kind where whatever value of x we have, the y value is just the square of that. So the question is, how do we get that? Well, what we need is a distance formula, right? The distance formula might tell us that if I have this distance r from the point xy to the point 2.5, what would that distance be? So, all right, well, you remember your distance formula. The distance formula is the one that goes that the distance between any 2 points A and B, or points 1 and 2 on a graph, is the difference in the x values, x2 minus x1 quantities squared, plus the difference in the y values, y2 minus y1 squared, right? And so we just basically are finding a right triangle solution right here. X2 minus x1, y2 minus y1, those are the vertical and horizontal distances of our legs, and the square root of that makes it a hypotenuse. So our distance, I'm calling it r in this case, Pirate's favorite variable. You know why. So what do we say? Well, r in this case is going to be the distance from that point xy along our graph. So we have x minus, let's see, the x value that we have in our point here is 2 squared plus y minus the y coordinate at our point, which is 1/2 in this case, squared. So we've got this function r. Now, right now, it's in terms of x and y. And what's typical in these kind of problems is that, well, if we have r, we want to express that in terms of only one variable at a time, not two, right? Right now, we've got three variables going on. We've got r, we've got x, and we've got y. So we need to replace one of these. I'm going to say, let's replace y. Why, you might ask? Well, we know that y can be replaced with x squared anywhere we see it in the function. So I'm going to replace that, but first I'm going to do a little bit of extra algebra right here. This is the hard part, right, is here. It's just doing the algebra. Let's carry it out. What I'm going to do is I'm going to go ahead and I'm going to expand. I have x minus 2 squared, which becomes x squared minus 4x plus 4. I'm assuming you know how to square a binomial by now. Plus, let's see what we have here. We'll have y squared. We'll have minus 1/2 y minus 1/2 y, so that's minus y, plus 1/2 times 1/2, that's 1/4. And you're looking at that going, oh, God, that's awful. Professor Peoples, what do we do with this? All right, well, what we're going to have to do is we're going to have to make a replacement. Sometimes to make a simpler thing easy, a harder thing easier, we have to make the harder thing harder. So what does that mean? Well, x squared minus 4x plus 4 plus, let's see, everywhere y is, replace it with x squared. So we'll have x squared squared. That's x to the 4th. Minus y is replaced with x squared. And plus 1/4, well, that's still plus 1/4. So let's simplify one more time. R will be equal to, let's see, the x squared terms go away. So x squared and x squared, those go away. X to the 4th, well, let's see, this is all under the square root. So I've got x to the 4th minus 4x plus 4 plus 1/4. I'm going to combine that together. That's going to become 17/4. If you need to pause this video and work out this algebra for yourself, please do so now. Okay. Well, I don't like fractions inside radicals any more than I like fractions within fractions. So I'm gonna get this out of here. I don't like 17/4 under here. So how would I do it? I would actually rewrite everything so that it was something over 4, right? Just make a common denominator. So this is really kind of like saying this. This is kind of like saying 4x to the 4th over 4 plus 6, sorry, not plus, that's a minus under there. Watch it, Professor Peoples. Minus 16 times x plus 17 all divided by 4. Again, if you need to pause to do the algebra, please do so. But this becomes a function that looks like this. Now I'm going to write it in a way that's a little more simple to find a derivative of. This will become 1/4 times the square root, which is the 1/2 power of 4x to the 4th minus 16x plus 17. Now, so that you're not drowning, I'm sorry, this is to the 1/2 power. so that you're not drowning in a lot of algebra right here. Let's go back. We're looking for the closest point. So what we're trying to do is we're trying to find a minimum. And that means, from what we've learned, we find minimums very often by finding where a derivative of a function is either equal to 0 or undefined. So, in our case, we can say the following. We can find the derivative of r with respect to x fairly easily right here. That's going to be equal to 1/2, I'll work it out with you here, times 1/2 4x to the fourth minus 16x plus 17 to the negative 1/2 power. And by the chain rule, we multiply that by the derivative of this inner part, which is going to be 16x cubed minus 16. All right, so dr dx, when we simplify this, and I'm not going to waste your time with a whole lot of algebra. Again, if you need to take a little bit of time to do this for yourself, you should. Dr dx simplifies as 4 times x cubed minus 4 divided by the square root of 4x to the fourth minus 16x plus 17 when we divide out 1/2 times 1/2 into 16, right? That's 1/4 of something times 16, that's 4. Dr dx is either going to be undefined or equal to 0 where our minimum is. In this case, we're actually looking for where it's equal to 0, right? So our derivative, dr dx, will equal 0 at the point where the numerator, in this case 4 times x cubed minus 4, is equal to 0. I will tell you right now that the denominator has no real roots. How do I know? Well, if I take that denominator and I try to set it to 0 and try to work through the numbers right here, over the set of real numbers, I'm not going to find anything that makes this 0. Right? I'm not going to be able to find the zeros very easily. All right, so let's take 4x cubed minus 4, the numerator, set it equal to 0, and solve where that happens here. So I'm going to do that all the way up here. Where does that happen? Well, 4 times x cubed minus 4 is the same thing as 4 times x cubed minus 1. I set that equal to 0. X cubed minus 1, well, the 4 doesn't really matter right here, but x cubed minus 1 factors as x minus 1. Remember, difference of 2 cubes, x cubed minus 1 cubed, times x squared plus x plus 1. Again, you can check, but the quadratic has no real roots, but x minus 1 does, and that's at x equals 1. And now when we look at this graph, it kind of makes sense. Sure, right here at the point where we have x equals 1, it looks like we probably will have that closest point of approach for the graph y equals x squared. So we can say that the minimum distance occurs at the point where x equals 1, and if y equals x squared, y equals 1, to the point 2 1/2.